Hello everyone, I'm Wengong Jin. Today I would like to present my recent work on domain extrapolation via regret minimization. This is joint work with my advisor Regina, Barzilay, and Tommi Jaakkola at MIT. So many real-world prediction tasks, such as image classification and molecule property prediction, require the ability to extrapolate to unseen domains. For example, in an image classification task, the model may be trained on a set of domains like photos, art painting, and cartoon, but it is tested on a new domain, sketches, which is totally different from the training domains. The problem is often referred as domain generalization, but here we recast it as domain extrapolation because I want to highlight the difference between extrapolation versus interpolation. So suppose the training set consists of n different domains or environments, E1 to En. Interpolation means the new domain E test falls into the convex hull of training domains. Here, the method can be those distributional robustness methods like group distributionally robust optimization. Extrapolation seeks a different types of generalization. Here, the new domain E test is outside of the training domains, and it's not just distributional robustness. It is more challenging than typical cases. So domain extrapolation is often tied to invariant representation learning. One way of domain extrapolation is to enforce an appropriate invariance constraint over the learned representations. So now suppose our model, we break our model into two parts. One is the feature extractor phi, which will elicit a representation phi x, and on top of that, we have the predictor f that predicts the label. So prior work has formulated this domain extrapolation problem in many ways. For example, domain adversarial network seeks to learn an invariance like this. So here the representation phi x is independent of the domain E. However, DANN often fails when the test domain has a very different label distribution. Conditional domain adversarial network seeks different invariance by incorporating the labels so as to overcome the label shift problem. So here, it requires the joint distribution of the representation plus the label to be invariant to the domain E. However, it still requires each domain to have a sufficient number of training examples per class. And we will see that this is actually a problem for many applications such as proteins and molecules. Invariant risk minimization is recently proposed to overcome these two challenges. Here, it seeks a new type of invariance based on simultaneous optimality. So specifically, IRM enforces the following invariance. So here, Y should be independent of E based given condition on the representation phi x. And it basically says it requires the predictor f to be simultaneously optimal in all domains. So suppose this LE is the loss of the model on domain E. Now we can formulate this IRM as a constraint optimization problem. Here we seek to minimize the standard empirical risk minimization objective, basically the sum of the losses across all the environments. And we require the predictor f to be simultaneously optimal within each domain. So here we can see that f should belong to the argmin of this loss on the environment E. Conceptually, the simultaneous optimality constraint should help domain extrapolation. However, is this really the case? If we zoom in a little bit closer, we can see that RM actually make collapse to empirical risk minimization. How is that happen? So now suppose we just we can rewrite the simultaneous optimality constraint as the follow. We can just rewrite the simultaneous optimality constraint like this. So if you look at this closely, if the model is over-parameterized, such as big neural nets, it's easy for the model to achieve zero training error in every domain. So the simultaneous optimality constraint can be trivially satisfied because now all the losses are simply zero. And since losses are always non-negative, which means this minimum is always non-negative. So as long as you can fit the whole training set, this simultaneous optimality constraint is trivially satisfied, and the model collapses to empirical risk minimization. Of course, empirical risk minimization may collapse to ERM in other scenarios. Now, in the paper, we did some further analysis based on additional assumptions. So suppose the environment E, examples X, and the labels Y follow the distribution like this. We define the representation as feasible if it retains all the information about the label Y. So it basically says the conditional Y given a condition on X and E should remains the same when we condition on the latent representation. Here, empirical risk minimization clearly seeks to learn a feasible representation. We claim that for any feasible phi x, its associated ERM optimal predictor F star is also optimal under invariant risk minimization. And the proof is in our paper. So how to solve this collapsing problem? Well, we propose to cast IRM constraint in terms of generalization. So here we replace the simultaneous optimality constraint over a different predictor F minus E. F minus E never sees this domain E, and it's trained on all the other environments. So here, since F minus E never sees this holdout domain E, this term, LE F minus E phi, represents the generalization accuracy of a predictor F on the new domain. Now, even if the model is over-parameterized, this predictor F minus E may still not generalize to holdout domain E. So this requires our model to extrapolate to new domains. And to be more specific, we can replace the simultaneous optimality constraint by a predictive regret. This is analogous to one-step regret in online learning, but cast here in terms of holdout environments. So we want to learn a representation that enables the predictor to be optimal against the oracle with hindsight access to holdout environments. So here, this is basically rewriting the optimality condition that I presented in the previous slide as the difference between the two losses. So here, since F minus E is never trained on this domain E, we call this term as a regret for the representation phi. So the overall objective now becomes the standard loss plus additional regularization defined by the regret. So we want the regret to be low because we want the model to extrapolate to new domains, even when it is not being trained on these new domains. To describe the forward path of our regret minimization, let's go through this simple example based on molecule property prediction. So here, the training set consists of n different domains, and in each iteration of our training process, we randomly select a domain as holdout domain. And our regret minimization can be cast as a 4-player game between the predictor F, the representation phi, and the two auxiliary predictors. So in the forward path of our model, we first train the holdout predictor F minus E on the training set except the holdout domains. So here, the predictor F minus E is trained on E1 to EE minus E, and it does not see the holdout environment EE. And we evaluate this loss here, and we update the predictor F minus E to optimize this loss. The oracle predictor FE is trained only on the holdout domain, and it minimizes the loss defined only on this holdout domain. To compute the regret, we evaluate the predictor F minus E that we have already trained on this holdout domain. And we compute the regret basically as the difference between the two losses. Again, by saying evaluate, I'm saying that this predictor F minus E is not going to be trained on this holdout domain. So f minus e will not be trained to optimize this loss because it should never be trained on the holdout domains. So for the predictor f and phi minimizes the loss of over all the environments, and the predictor f is trained on all environments, and we use f at the test time. The representation phi is regularized to elicit predictors that extrapolates to new domains by minimizing this regret objective. So in the backward pass, just note we can optimize everything using gradient descent, but just to note that inherently our objective is an adversarial game. So FE minimizes the oracle specific loss and thus increases the regret. Phi minimizes the regret instead. And we can solve this adversarial game by in one go using the gradient reversal trick. So we can backpropagate the two competing losses in one go using this gradient reversal layer between the feature representation and the predictors. So this method works well when we have few domains and each domain has many samples. However, in real practice, such as molecule property prediction and protein classification, this has additional challenges because the domains are defined combinatorially. So here, for proteins, the domains are defined by protein superfamilies, which represent evolutionary groups. The domains are combinatorially defined along the evolutionary process, and there can be more than 1,400 different domains for a small dataset with only 10,000 examples. So here, 70% of the domains have less than 10 examples. A more extreme scenario happens in molecule property prediction. Here, each domain is defined by a scaffold, which is a subgraph of the molecule, which represents the backbone of the molecular graph. Again, on a small dataset with 10,000 examples, we have 1,600 domains, with 75% of domains having only one example. So this is problematic because given a single training example, the model cannot tell how the domains are defined. So the domains becomes non-identifiable for the Singleton domains. The model would see any variation from one example to another as the nuisance or the domain shift. For example, the model may perceive the domain as indexed by any substructure, and number of domains now collapse from 4 domains to 2 domains because the Singleton domains domains become non-identifiable. So our solution is to explicitly incorporate the domain semantics such as scaffolds or protein superfamilies. So how to incorporate these domain semantics? Our solution is domain perturbation. So this perturbation will inform the model where the domain variability comes from. We introduce a domain classifier G, which operates over the representation phi x, which predicts the domain of the input x based on its representation. So here the output could be protein family or molecular scaffolds, and the domain classifier minimizes the domain classification loss with respect to the ground truth domain label. So based on this domain classifier, I can perturb the latent representation phi x using the gradient delta x, which comes from this domain classification loss. So this will give you a set of training perturbed examples, phi x plus delta x, which informs the model where the domain variability comes from. So this variation between the perturbed example and the original examples highlight the domain variability that the model should not pay attention to. So it should not affect the quality of our prediction. So how to enforce this? We can again use our regret minimization method. So here we add additional regret term r phi plus delta to encourage the model to extrapolate to perturbed examples as well. So now the new objective basically has additional term r phi plus delta defined over the perturbed examples. Here we have the standard regret minimization defined on the original examples. We have RGM over the perturbed examples, where we use another oracle predictor Fe delta that is defined on the perturbed domains. So how these methods actually works, we did 3 sets of experiments to validate our model. First, we did a synthetic experiment on a 2D moon problem to compare invariant risk minimization and the regret minimization. Here, the domain shift is caused by rotation. So we have, in the training set, we have 2 domains. The original moon with the moon rotated by 20 degrees. Since a validation set plays a crucial role in domain generalization, we consider 2 different ways to construct the validation set. In the in-domain validation set setting, we simply add the Gaussian noise on the 2 moons. On the out-of-domain validation set, we instead rotate the 2 moons by 40 degrees, and as you can see, the out-of-domain validation set closely resembles the actual test set, where the examples are rotated by 60 degrees. So here is our result. Regardless of in-domain or out-of-domain validation, our model regret minimization does a lot better than ERM and IRM on the test set. If you can see on the right-hand side, we have this plot which shows that IRM collapses to ERM when the model achieves 0 training error. We do this by just lowering the L2 regularization. So here, as you can see, when the L2 regularization is small, all the models achieve like perfect training accuracy. However, empirical risk minimization and invariant risk minimization performs poorly, while our model maintains good test accuracy even with this 0 training error. So we also did some real-world experiments on protein homology classification. Here, the training set and validation set and test set are split based on the protein superfamilies. So here, the training set consists some superfamilies, while the test set consists of different types of superfamily. So this requires the model to generalize to a new set of protein space. The model is a simple transformer that takes the protein sequence as input and predict its homology label. It is a 1500 way classification, and as you can see, the top 1 accuracy of our model does much better than other domain generalization techniques. Our model extrapolates better to novel protein spaces. We also did another set of experiments on molecule property prediction. Here, the training, validation, and test set are split based on molecular weight. The training set consists of small molecules, while the test set consists of much larger molecules that is also more complex. So this requires the model to generalize to new chemical spaces. We tested our model on molecule net benchmarks. As you can see here on 2 of the datasets, our model achieves much higher classification accuracy than the previous domain generalization paradigms. Lastly, we also did some experiments on the COVID-19 antiviral prediction. So here, the training set, validation set, and test set corresponds to different data sources related to COVID-19. So here, the model needs to overcome the dataset bias induced by different screens or different datasets. And as you can see here, our model does significantly better than other domain generalization methods, and we hope this is useful for COVID-19 research. So just as a summary, many real prediction tasks require the model to extrapolate to unseen domains. And we need to learn the representation that enables the predictor to be optimal against the oracle with hindsight access holdout domains. Our regret minimization paper can be found in this link on arXiv. Really, thank you for listening to my talk, and I'm happy to answer any questions under the YouTube channels. Thank you very much.